So we are in the portion of this course that's called production theory. We're thinking about firms and the structure of production, and eventually or progressively we're going to work towards the cost for producing goods and services, right? But it all starts with what we call broadly the technology, the way in which firms are transforming capital and labor into the output. And at this point, we're in a simple setting. Each firm is producing a single good, right? And all of that can be expanded into multiple sort of products. And sometimes you see these types of things as homework. Sometimes you do research on a topic and you're required to think about multiple products. So depends how you get introduced to all of these extensions, depends on the context. So what we stopped at last time, we were working on an example. So I'm going to write here example continued. And we had this production function Q is equal to f of k, comma L, lowercase, is equal to 600 k L squared minus k to the L to the power of 3. Okay, that was our production function. We defined the short run. So you would say that this is a long run production function. And if you wanted to do short run, you need to pin down one of the inputs to a specific amount, right? I have 1 unit of capital, 10 units of capital, 500 units of capital, and I can't change that in the time period that I'm thinking about. So we said let equal to 1. That's very convenient for us, right? In order to be able to do all of these calculations. So then Q is going to be equal to 600, K to the power of 2, that's 1 to the power of 2, that's 1. That does not need to be in here, right? So L squared minus K to the power of 3 to the power of 3, that's 1. We can skip that, L to the power of 3. And then we did a variety of things. If you go back in your notes, we asked the question of where is Q actually maximized with respect to labor, at which point, what level of labor that's being hired are you going to maximize your output, right? You have to maximize a function. That's why you do calculus earlier in this program. And then we developed an expression for the marginal product of labor, the average product of labor, and I believe we explored those things as concepts. So what did we have? We had L, for example, expressed as del Q over del L is equal to 1200 L minus 3 times L squared. And then we proceeded for that APL, just I'm going to write it down, is equal to Q divided by L, how much output divided by how many workers in aggregate you have. That was simply this divided by L. So that would be 600 L, actually the short run version, minus L squared. So if you plot that, and I'm going to do that sort of in a very general way, sort of a textbook way, you see typically something like this. So what is the argument here? The argument here is labor. So on the x-axis, you're going to see labor. Oh, yes. Thank you for letting me know. If I forget, please do tell me. And so how do you plot these functions? These are both functions of L. So you're going to have L on the x-axis, right? That's your effectively decision variable. And what is going to show up on the y-axis? Generally, the product that comes out from employing labor, which we symbolize as Q. So it's worthwhile noting that the marginal product of labor is some level of output, right? The average product of labor is a product. The Q is the total product, right? So how much it's going to happen, it's going to come out from this production process. So you could say over here on the left axis, if it helps you to think about this, you can say, oh, yes, you can put the total product here. You can put the average product here. You can put the marginal product here. Okay. Generally, you can write this as Q, right? Because all of these concepts describe some quantity of the good that is being produced. Does that make sense? So generally in microeconomics, whenever you want to draw something, put it in a diagram, always think what is on the x-axis, what is on the y-axis. Am I truly clear about what these quantities are? Are they expressed in units of something? What is that something? Labor, output, like final good. Is a dollar figure somewhere in there? Are you representing value, or is it physical units? Okay, so think about all of those things. So if you wanted to draw a marginal product and average product, you can do that on a computer to sort of have these accurately, but you can do something like, oh, you're going to have marginal product increasing, getting maximized, and then starting to decline. Okay, you can say this would be your marginal product. And then at some other point, and given the behavior of the marginal product, you have a specific behavior for your average product. Let's say your average product, we saw before, gets maximized at, let's say, at the level of 300. The marginal product, again, from, this is 300, 200, 100. Oh, sorry, I'm going to fix that. 100, 200, 300, not to scale. The average product is going to also be maximized at some point, and your diagram is going to look something like this. So I'm drawing this over here. Let's say this is 400, again, not to scale. I'm drawing this just to denote something about the relationship between the marginal product and the average product. The average product is always going to be increasing as long as the marginal product is above the average product, right? So if the marginal product is higher than the average product, then the marginal is effectively pulling the average product up. Does that make sense? The equivalent of getting a better grade in a semester, in a course, and that increasing your grade point average, right? If on the margin, the additional course is higher than your grade point average, is going to go up. Same thing here. If the marginal product is above the average product, as the curve shows here, right? So this is marginal product above the average product, then that's going to be pulling the average product up. At the moment that they cross, right, the average product is equal to the average, the marginal is equal to the average over here, but then that curve is below the average product. So if the marginal product is going to be below the average product, it's going to bring the average down. Same thing with, that applies with any concept of a marginal and the average. And the grades in the college setting is the easiest sort of thing to understand here. So we can say, and that is sort of behavior that let me write a couple more things. So 300 output per worker is highest, right? That's where the average product gets maximized. The interesting thing about the marginal product, that curve can also be extended below the figure, right? This point over here at the marginal product of 400, what do you have? What happens when the marginal product becomes zero, when it hits that axis? So far you've been hiring workers, right? On the margin, they were giving you more product, but that kind of declines the amount that they give you. What happens at MP being equal to zero? Correct. So what is the quantity that is being affected here? Yes, the marginal product is being affected.
Output per worker. No, your increase in output per worker is being affected.
Right. How about the total output? What's happening to the total output for your firm when marginal product is zero? Yeah.
Staying the same.
Right. What's going to happen if you increase labor to the total output? Right. What if you decrease labor? Yes. So you have maximized your total product, right? The total output that you produce has been maximized here. I haven't plotted the production function too, which would have lived in this diagram, but it would be much higher in the figure, right? I'm only plotting two of those things, right? The total product is not. But at this point, if you extended that point upwards, you should be finding the maximum of your total product. As an exercise, you can take this function and these marginal products and average products, plug them into a statistical software package and plot them and take a look at those graphs. having had some experience with plotting functions, and there's function plotters, there's scientific calculators, there's web applications. So if you want to see that drawn accurately or to scale, you can plot those so that you can see that behavior. So I'm going to write this over here. So I'm going to say because k is constant, and it doesn't matter what value we set it at 1. We could have set it at any point, any value, and you have and the marginal product of labor is diminishing for the reasons that make sense intuitively and mathematically, given the functional form that we are employing. Eventually, right? Not always. We see a declining level of output per worker. Eventually, right? Not in the beginning of the production process. And that is going to be defined by the functional form that we pick. Or in our case, the manufacturing engineers tell us that this is, we looked at the data and we fit the data, and this is sort of the functional form that we're dealing with given our technology. Okay. But this reflects the sort of the marginal product being lower than the average product and bringing it down eventually in the as you hire increasing amounts of labor. So that is sort of how you can sort of work through a production function, right? So you're given the production function, calculate marginal product, average product, plot it, and then if you want, you can also plot the total product, which I have not plotted here, right? Which in terms of sort of the scale, it explodes up here. So these two curves would be dwarfed compared to the total product function. So that's the situation for the sort of in general terms. That's the situation for the short run. It should not generally be challenging. A derivative with respect to one input of production, sort of not a big challenge mathematically. And sort of the main principles apply here: diminishing marginal product of labor, and sort of you see the effects that you observe. In order to think about the long run, we need to return to the production function with the two inputs and work our way through sort of the partial derivatives and sort of think about how we can do the analysis at that particular level. So that follows next. So for the long run, I'm going to incorporate some additional concepts, right? We talked about the marginal product of labor, the average product of labor. We're going to talk about those things that we call isoquants. So isoquants, so if you want to decompose the words here, iso is something, it's a Greek word. It means the same or equal. And the word quant comes from the word quantity, right? So I would say here, would expand that. So essentially, you translate that as something that shows the same or equal quantities. And it actually is a function, right? It's something that you can plot, and it's going to be a function that shows the same quantities of output. Okay? So I'm going to say here in general terms, this is a function that shows all points of that line, right? Equal quantities of output. That's what we symbolize as Q, given K combinations. So this is the same concept as what that you did in your first semester in microeconomics. Level curves that how do we right showcase the same level of utility across all points. And where were these curves being? Well, what is their formal name in consumer theory? That's their slope. But what are they called? They're called indifference curves, right? Yes. So this is the equivalent concept of an indifference curve that shows you the same level of utility that you can get with different combinations of goods that you could be purchasing. Correct? And they map your preferences for any level of goods and any goods that you might be thinking about purchasing. Obviously, then you realize that, well, I can't buy all of these bundles, right? Because I have a specific amount of income and I'm constrained. So then you introduce the budget constraint. So here you have a very similar story, right? So you have this curve that shows the amount of output that you can produce, and typically you will see that they have a very similar shape because we're using the same functional forms to represent preferences and technology. So same amount of output that a firm can produce by using different amounts of capital and labor. So the notion that we're trying to capture here is that you can have a lot of workers working with a little bit of capital and produce, plates or anything, sort of ceramic or whatever it is. Or you can have a lot of capital and very few of workers and have sort of a different process that is going to produce the same amount of output. And something is going to tell you what decision you're going to make, right? Some conditions in the market typically are going to, or depending on where you are in the world, level of economic development, is going to tell you whether in your production you're going to be labor intensive, you're going to be using a lot of workers and a little bit of capital to be producing, let's say, 100 units, or whether you're going to be capital intensive, right? You're going to be using few workers, but a lot of capital, right? But the idea is that a production function is telling you all of the different ways through which you can produce a specific amount of output. And that output can be 100 units, 200, 300 units, and we're going to have these level sets effectively describing this. So in the words or in the language of math, these are called level sets. I like to think about them as, I like to think about them as contour plots in cartography, right? So all of these maps that you have seen before that showcase elevation, sort of, I don't know, there's multiple names for those. Same thing for oceans, right? Depth sort of maps. These are sort of contour plots. Okay. So the official definition that we're going to use in microeconomics goes like this. So you say for any fixed level of output, and we're going to call that Q bar. You would typically put a bar on here to denote that we have fixed that, right? The set of input vectors producing Q bar is called the Q bar level isoquant. So the set is as follows: X belongs in the space of positive Rn, right? You have n different inputs, taking positive real values in particular, such as the f of x is equal to Q bar, right? So you're defining a set of x's such as the production function is equal to a specific level of Q. So this is called the Q bar level isoquant. Okay. It is simply a level set of function f. So if you think about this particular example, you have an f function with two arguments, capital and labor, or x1 and x2. If you plot this in 3 dimensions, right, you're going to have some sort of a surface, right? So the level set, how do you derive it, is you pick a specific q, like your z-axis, right, and you cut across the function, right? And what is sort of this intersection of a horizontal plane with your 3-dimensional surface? It's going to be a line, and that line we call the isoquant. It's sort of your level set, right? So that's sort of a mathematical construct. Cool. Any questions on the nature of the isoquant? It should be a familiar concept given your exposure to microeconomics before, because it's a sort of an equivalent concept to the indifference curve. So let's get back into the production example. So I'm going to say here back to the world instead of the n input world. So an isoquant shows the combination of capital and labor combinations that can produce a given level of output, Q bar. Okay, hopefully that makes sense. So f of k comma L is going to be equal to a Q bar. The reason for this is showcasing the possible substitutions of one input for another. And this is really important for economics, right? Because you talk to folks in a variety of fields, and somehow you get a sense that people cannot sort of conceptualize this possibility for substituting across inputs, right? So you're not, in the long run, you're not stuck with sort of a particular combination of capital and labor. You can substitute across them, and as economic conditions change, we're going to see sort of how cost comes into play here. Cost for hiring those inputs, that's going to define what this firm is going to be able to do in terms of substituting across those inputs. But at this point, we're just in the theoretical possibility, right? We're not thinking about how much does it cost to hire labor, how much does it cost to hire capital, how much total money do I have to spend towards labor and capital, right? So it's just the theoretical possibilities for production at this point. So I'm going to say illustrates the possible substitutions of one input for another. So I'll make a drawing here for you to see. Again, two axes, that's typically the case every time that we're going to draw. What do we need to think about? Where are these units going to live, right? So what are we going to plot on the horizontal axis? What are we going to plot on the vertical axis? Before, in your consumer theory portion of microeconomics, you thought about indifference curves and the space in which the indifference curves lived. So what was that space? Do you remember? What did you put on the two axes when you were plotting indifference curves? Yes, it was the goods that you were thinking about buying. So here it's a similar decision problem. Here the firm decides not how, like the consumer, how many, what quantities of goods you're going to buy, but it decides how much capital and how much labor it's going to hire. So we're going to traditionally put labor on the horizontal axis and capital on the vertical axis. You can choose to go your own way, but this is going to change things in your analysis, right? If you're going to try to plot it diagrammatically. So generally try to follow conventions. You don't plot the price on the horizontal axis, right? It's like this, like a convention economics. You could, but that's going to change the way that you're going to be presenting things, and it will confuse a lot of other people. So just try to stick with that sort of convention, if you will, right? So then we're going to plot the isoquant, which is going to be a curve that lives in this space, and assuming a specific type of production function, the isoquant could have this shape for a particular level of, for a Q bar, that it could be equal to, let's say, a specific value. You don't have to put numbers here. That would mean that you can produce, let's say, Q bar level of total output, 10 units, with a combination of L and K that is up here. So that would be, let's say, an L1, and that quantity would be a K1. Or you could be producing that Q bar equals to 10 with much more labor, let's say L2 units of labor, and let's say K2 units of capital. Obviously over here, K1 is greater than K2. Over here, L2 is greater than L1. That is combination, if you will, one of inputs. That is a set of inputs that you call two, whatever you want to say. Notice here what is happening in terms of the capital intensiveness or the labor intensiveness of the production process. So let's look at the first combination of capital and labor. What you would call that point, that of a choice of hiring inputs.
High capital, low labor.
High capital, low labor. So can we call that capital intensive? Yeah, we can call it capital intensive. That's one way you're going to see it in the literature. The other way that you're going to experience that in texts, people would be talking about a high capital to labor ratio. So this is typically the choices that sort of advanced economies sort of will typically operate in. If you thought about sort of the aggregate, here we're talking about firms, right? So it's a little bit of a different story, but these kinds of diagrams you also see in macro, in economic development, in a lot of other fields, right? Talking about aggregate quantities of capital. Well, let's take a nation and add up all of the K. let's take a nation and add up all of the labor. That's how you go from microeconomics to sort of macroeconomics, but you have similar sort of diagrams to work with. Obviously, on this point, right, that will be here. What would we write over here? Similarly.
Labor intensive?
So you would have labor intensive technology, you can define that, or a low capital to labor ratio.
And for nomenclature, you always say capital first?
Yeah. Typically, yes, another sort of convention. It's not a labor to capital ratio. It's usually a capital to labor ratio when you talk about those types of things. And it starts from where in these diagrams where you put capital, where you put labor too, like that helps also. So people would write high K over L. That's the capital to labor ratio. So that's the structure of things. And then you can choose to say, well, what would be the situation if I had a higher Q bar, right? If I was aiming for a different level of production, right? We're ramping up production. We go from 100 units or from 10 units to 20 units to 100 units to 1,000 units. For each level of Q, you can have an isoquant as it's predicted by the functional form that you've used. Because think about sort of these functional forms, they're not limited in terms of the extent of labor and capital. If you can think of a number and you can plug it in, a number for L and a number for K, no matter how unrealistic it is, you can have a Q. Right? That's the beauty of the mathematical function. Now, you can debate about, well, how far can we extend this production function, right? This form, if we have data up to using 1,000 workers and 1,000 units of capital, can we extend that mathematical production function to 5,000 units? Or does it change? Does that kind of function capture the full range of production possibilities? But at this point, we're working on the basis of a math function, right? Discovering what it is exactly at different units is a different story, right? Maybe you need to use statistics or econometrics or other things. So if you wanted to represent a higher production function, then you could plot another isoquant, right? Similar idea here, where a Q bar now could be a prime equals to 20 units, and so on and so forth. Also, fewer units of production, of total output, if you will, those curves would fall below this curve of Q is equal to 10. And similarly to indifference curves, there are specific properties for those production functions, for those isoquants. They cannot cross for obvious reasons. And there's a few other things that you will see about them in your textbook. I want to talk about the slope of those curves. So the slope of the isoquant, what does it show? You have the example of the marginal rate of substitution from consumer theory. It was capturing a specific sort of idea or property of those utility functions. Similarly, for the isoquant, what do you think it's going to be capturing?
I remember concavity.
Not necessarily, I'm not asking, mathematically, it's a derivative. But what does it like as a concept? If you were to walk along one of the isoquants, what would you be calculating
Or maybe
between the units of labor and the units of capital that you are using? Right, you're essentially right to keep the Q the same, right? You're saying, well, if I reduced or if I increased labor by a little bit and wanted to stay at the same level of output, right? What would be the equivalent? What would be the K that I need, right? So, what kind of a trade off would I be making? What kind of a substitution? What is this slope here? What is that substitution, that needed substitution up here? Is it high or is it low? Essentially, what I'm asking is it high slope or is it a low slope, a small slope? Yes, that would be a high slope. So if the substitution amount would be significant up here. So in order to increase the amount of, or you could increase the amount of labor by 1 unit, you would be reducing capital by a lot, right? Here you would be increasing the amount of labor by 1 unit and not substituting capital, right? So let me define this in words. So I'm going to say it shows the rate at which labor can be substituted for K while keeping Q constant.
Further along, so I think you said that earlier that we're not going to quite get into that yet, but obviously the prices of each price ratio is going to depend. That's what we're going to do that later.
So we're building on technology. So the question is, when do prices come in for the inputs? And they come in when you actually have to make a choice. Because right now, theoretically, that I can use this much K and this much L and produce this much Q. But in the end, how are you going to make that decision, right? As a firm, how much K and L are you going to, and all of the other N resources, right? Inputs in the production process, how much am I going to purchase? It will depend on the prices that you're faced with in the markets, right? For labor, for capital, for a natural resource like natural gas, oil, solar, and so on and so forth, right? And that becomes part of your optimization problem, right? You're given the prices, assuming that they emerge from a market, right? And you don't have any influence. So these are perfectly competitive firms, right? The price takers, all levels, right? Also, we'll see how the price of your output matters in the profit maximization side of things when we get to that. But so we're moving towards cost considerations. But before we think about costs, we're thinking about, well, what is theoretically possible? Right? That we're not bounded by how much money we have, right? Also, the question of where are you getting the money that you need to hire those inputs, right? Are you working on the basis of a loan? Where does it come from? Do you have a specific, in microeconomics, it's called outlay or expenditure towards inputs that you're making? Okay, so we'll see how it all comes together.
It dealt a lot with the cost of capital, and it's like, oh, you can choose a loan, and so put the cost of the loan in the optimization problem.
And again, when you go into the practical aspects of sort of the expenditures that are happening, it can become a much more specific problem.
Yeah.
So what are we going to be talking about here? In particular, yes, this is a negatively sloped line. So we're going to be thinking about the absolute sort of amount of that slope. So we're going to say that the absolute value of the slope is called the marginal rate of technical substitution. So we're not going to call it the MRS. We're going to call it something different to distinguish it from what you did for consumer theory. So the absolute value of the slope is called the marginal rate. It is a slope after all, right? So it is a derivative. So it's the marginal rate of technical substitution. We symbolize that as MR, and we can sort of work out the math for the case of the two goods, and you can do the same thing for N goods. Let's do that next. So I'm going to say for N equals 2, your set of X's, right, your set of inputs is going to be X1 and X2. And the MRTA, it's going to have subscripts, say 1, 2 of X, so that you can read MRTS of X2 for X1, okay, is obtained by totally differentiating. So you have your F function, right? It has two arguments, Fx1, X2, and you've set it Q equal to a specific value. So always remember the starting point for even thinking about an MRTS has to do with setting Q equal to a specific quantity, because Q is not going to change. You've decided on an output. This is how much we're producing, 100 units. That's not changing. Now let's see how we can substitute labor and capital and at which rate we can do that, right? So over here, we're going to say, well, how do you totally differentiate this expression? You can say Q bar is going to be equal to the partial derivative of your F function, x1 comma x2, first with respect to x1 times dx1. So that's your standard expression, plus the marginal effect, so the slope with respect to x2, So that will be del f x1 comma x2 del x2 dx2. So the idea here in total differentiation has to do with, well, if you're going to think about the change in this value, you could be changing x1 by a little bit, or you could be changing x2 by a little bit, right? Because it has the f has two arguments. Well, if you change x1 by a little bit, well, how much is the value of the f going to change? If you change x2 by a little bit, how much is the value of the f going to change? This is going to define how much your f is going to change, symbolized as q. But guess what? We are keeping q constant, so we need to set this equal to 0, right? Because we really do not want to change that q. So this is set equal to 0. So remember this. That's how you work on an isoquant, because you keep the total production the same. Okay. So does this total differentiation expression work? Right? We're essentially thinking about, well, yes, both x1 and x2 will have to change in order to stay on the same curve. We need to take into account the slope, right? The partial derivatives with respect to x1 and x2, and all of this needs to be equal to 0, because we don't want that dq to have any positive value or negative value, right? We want it to be equal to 0, because we live on a single isoquant, and we're trying to calculate the slope of that thing. So that means, right, we have an equation here that we can solve. And also remember from your math that I can express this. I don't want to rewrite this. So how about I call this f subscript 1, and how about I call this f subscript 2, the partial derivative with respect to 1. So when we have capital and labor, f subscript k, f subscript l. Yeah. So we're going to have f1 dx1 plus f2 dx2 is equal to 0. That's essentially what we've written up here. And how can I sort of convert this to denote sort of a derivative, which is going to represent the slope? We can pool the dx's on the one side and the other sort of things on the right hand side, right? So the dx is on the left hand side. We work through this problem and you can get to, let's see, what would be the better way of doing that? So you could say f2 dx2 is equal to minus f1 dx1, which means that if we divide by dx1 on both sides, we're going to have f2. Let me bring also the minus sign on the left-hand side. f2 dx2 divided by dx1 is equal to f subscript 1. So essentially, I multiplied by minus 1 on both sides. And then divide by f2 on both sides. I'm going to have this expression of dx2 dx1 is equal to f1 over f2. So that's sort of the expression that we are arriving at. The other thing that you can be doing here notation-wise, and something that people usually do, is the add a vertical bar next to the derivative, and this acts like a sort of like a caveat. So we're thinking about this trade-off between x1 and x2, given that q is not changing, right? So here is dq bar is equal to 0. So in order to make this look a little bit more like economics, I can rewrite this. This is equivalent to saying that this minus dx2 over dx1, so that's the slope, the MRT is equal to, well, what would be f subscript 1 as an economic concept? F is a production function. What is f1? Of input 1, or we don't need to define it, right? So it's the marginal product of input 1. Okay, so MP subscript 1, and obviously F2 is the MP of input 2 in general terms, right? So all that we did, again, to summarize, is employ the concept of total differentiation to this general functional form and sort of make that change equal to zero, right? Because we want to stay on a particular level set. Okay, that's all that you're doing here. And then you work through the equations, and this is what you get. So when you do intermediate microeconomics at the undergraduate level, this is given to the students as a formula. So people, again, it depends on how much math you want to show them, but they're like, oh, you have these isoquants and the slope is given by this formula. There's not as much sort of questioning about where does it come from. It comes from math. It comes from calculus. You have a three-dimensional surface. You found the level set. You can do the math that sort of gets you to that particular formula. But it becomes very useful for thinking about operating through sort of problems and understanding this idea of how much can you substitute, how easy is it to substitute between labor and capital, what are the actual technical needs when it comes to substitutability. No cost considerations just yet, just how technically feasible is it at this point. What are sort of these needs for substitution? Okay. So I'm going to expand this for n greater than 2. When n, let's say, is greater than 2, for any inputs I that is different than j, the MRTS is going to be equal to the marginal product of I over the marginal product of j. And according to the way that we sort of wrote this, so what would we say here? How would we describe this MRTS? Notes. 1. Isoquants must be negatively sloped. Marginal products are non-negative. Those make intuitive sense. Isoquants are convex, which is going to imply that the rate of technical substitution, the MRT, is diminishing. Yes.
Eventually, is your marginal product.
Could it be negative?
Right.
Yeah, we've seen some short-term production functions where that happens, but it does not make sense that you would be hiring.
We're just doing this in real life.
They wouldn't. Yes. So I had a professor when I was an undergraduate, and he was showing a production function, right? And it's upward sloping because you hire labor and product goes up, and then you have diminishing returns, and it starts to flatten out, and it reaches sort of the maximum product. And he's like, why do you want me to draw the rest of it? Right? Why do you want me to draw the downward portion? That just doesn't make any sense. That it's like, yes, it exists mathematically, but I'm not going to even draw that. Okay. Does that sort of make sense for why? So an economist would be like, this is the mathematical structure, but does the math make sense? Sort of thinking about the world as an economist is not all sort of. So obviously, sort of in math, you see functions extend to negative sort of values of the x. We're not drawing those in economics, right? There's no notion of negative output, or there are some cases of sort of, if you think about negative interest rates, where some of these functional forms might be typical. But again, you saw the definitions. We're defining these values on the positive Rn space. There is an argument for why you may want to not be drawing things beyond the specific point if it does not make sort of economic sense. That is assuming rationality, right? So we're assuming that these firms are perfectly rational, perhaps, and they would never be moving towards areas in these figures that don't make sense, right? Hiring more labor when you see your output decreasing. And then the negative slope of the isoquants denotes sort of that substitutability. That's sort of the idea of non-negative marginal products, sort of the convexity of the isoquants and the diminishing, essentially, MRTS. That's something that we can explore a little bit further. And the fourth node has to do with the second partial derivatives, the f of marginal product of labor differentiated with respect to labor, and the marginal product of capital differentiated with respect to capital being negative also eventually. So in our notation, let's go back to, instead of using 2 and 1 and I and j, let's go back to using capital and labor so that we can talk about those things more concretely. So let's use n is equal to 2. You have two inputs in the production process, and k and l for the notation, and rewrite the MRTS. So the MR of labor for capital is going to be the marginal product of labor divided by the marginal product of capital. So essentially what we're seeing here is that this is the minus dk over dl. So you see how this sort of works out. When you take a derivative of capital with respect to labor, remember your diagram here, right? So you plotted k on the vertical axis and L on the horizontal axis. You have this curve over here, this isoquant. So you're at the specific point. What is the slope? So that's why we can express this as k over dl. We know that that slope is going to be negative. By adding sort of that negative sign, we can talk about the slope in sort of in absolute terms. So that's sort of a way for you to think about, well, what is the marginal rate of substitution? Is how much is k going to change as we are changing labor, right? We're adding a small amount of labor. K is going to go down by a lot. We're adding this amount of labor over here. K is not going to drop that much. That's why we're also saying the marginal rate of technical substitution is diminishing. It's really high up here. It becomes low down here. Okay. You can do a variety of other calculations when you want to think about, so in particular, a diminishing MRTS. How would you do this analysis? Well, you would take the MRTS and take a derivative with respect to labor again. So let's say if you wanted to look at how the MRTS slope changes for KL, this is simply the derivative. What is the MRTS? Oh, I wrote it as the marginal product of labor and capital here. I can write this as F subscript L. What am I doing? Over subscript K. So here I would say, well, whether we're differentiating the MRTS, well, the MRTS is F subscript K dl, right? And then do some calculus, right? Which I will sort of upload some notes for. So you don't have to we don't have to do all of the math here, because think about, you have a ratio. Both f of L and f of K are functions of both K and L, right? So you would have to do sort of some additional derivatives here, and working through the math, get to sort of a final result. So if you do this, and we avoid the dots, then you get this expression over here. I'm going to try to do this right. F of K squared times FLL minus 2 FL, marginal product of labor. All of these things have names, right? K plus K times FL squared divided by FK to the power of 3. So if you look at this expression, you can start thinking about the signs here, right? So what is the sign of the marginal product of capital squared? Well, that's going to be positive. What would be the sign of the rate at which the marginal product of labor changes as you are adding labor? So that marginal product is going to be coming down, and so on and so forth. You're going to be sort of examining the different signs of these quantities. So eventually there is a few things that need to happen if you want the derivative of the MRTS with respect to labor to be negative, right? So eventually you can see that if the marginal product, the rate of change of the marginal product of labor with respect to capital is positive, that is essentially what we're saying here. As you increase capital, that means that the marginal product of labor is going to be going up, right? So if this is happening, then you can expect the del of the MRTA of labor for capital to be negative. But on the other hand, if this particular derivative, which is the same derivative as the FKL because of Young's theorem, right? You remember from your math, is less than zero, then you are not sure about the value, right? So there are some conditions that need to be met over here. It could be greater than zero or it could be less than zero. So generally, we will consider, without going into a lot of details, that f of KL equals to this to be greater than zero as a sufficient condition for diminishing MRTS. And I will leave you with this. We're going to talk a little bit more about isoquants when we come back in the next lecture. But sort of this ties in the concept of, well, how does the marginal product of either capital and labor behave as we're changing the other input? And we need to be making some assumptions for these functional forms that we're using so that there is logical consistency, right? Diminishing MRTS means that these functions are convex and they are sort of what we call well-behaved in economics, in the same way that you were using sort of well-behaved functions when you were doing utility, like the consumer theory part. So that's all for today, and more on producer theory when we come back.
So every time I've been exposed to it at ESU,